So I'll get started. I'll first of all do an introduction. On the call with me is Stephen Holloway, also from Renesas. He's been at Renesas for about 13 years and is one of our experts in verification and UVM. Steve is part of the UVM Accelera working group and worked with me co-authoring the code that has now formed UVM mixed signal. He's an expert in like formal and other aspects of verification, and I lean on him quite often to guide me on pure digital based stuff. He's a member of he's a senior member of technical staff here as well. Myself, I'm sort of a mixed signal verification engineer working mainly on methodology. I also have worked with the UVM mixed signal standards, which should be out soon. I'm also chair of the System Verilog / Verilog AMS working group and part of the System Verilog MSI group, which is the replacement for Connect modules. Also been at Renesas for about 14 years. The way this presentation is going to be run is Stephen will be presenting some slides and I'll be presenting others, and we might interchange it to make sure certain key points are given as we go through. Please add questions to the Q&A and we'll answer them at the end. And at that, I think we'll just get started so we don't waste time just looking at the first slide. So over to you, Stephen.
Thanks, Peter. So really, as Peter said, this is a sort of a presentation of two halves, really, and we're going to focus on two aspects that you really need to put in place to do constrained random verification. One is the stimulus side, how you actually generate your or you constrain your stimulus in a sensible way, and the second part is then how you then implement your independent checking, your monitoring. That's a particular bit of technology that Peter's been working on, which he'll go into some detail in his mixed signal monitor. And we'll round up on, we'll conclude on some points in basically that all of this stuff here goes into the UVM-MS standard, really, and that's the thing that will drive it forward. So if we look at try to compare directed testing with constrained random, we show a canonical picture of some directed test setup where we have a stimulus, some kind of test sequence, and which we're driving into the DUT, and then we're basically checking against some expected response. All of this is sort of hand cranked stuff, and typically the expected response isn't going to be a file to compare or a set of ones and zeros, but typically what we do is we have inline spot checks that are sort of interwoven in the stimulus file or the test case. So that's quite a common sort of setup that you might see when people do directed testing. So in order to do that, first of all, you'd have to work out what scenarios we need to check the expected functionality. Next, Peter. Sorry. Then, yeah, thanks. Then we'd have to create those tests, one by one, and the completeness in terms of verification would be based upon pass-fail state of those tests, and potentially code coverage is another metric we could use to assess our closure. But the big problem with directed testing is that by definition, unexpected scenarios are not covered, and typically that's where bugs are, in the things you don't think about, or the interaction between parts of your design that you haven't thought about properly, and that's potentially a large hole in your coverage. So if we look at the setup that you might find in a constrained random test bench, we'll have some method of generating random stimulus. Of course, this is not completely random. That would be quite useless. It'd have to be sensibly constrained, but in essence, it's random. We have to then have an independent checker because we don't know up front what the stimulus is going to be, so we can't have any expected responses woven into the stimulus stream. So we have an independent checker that's sitting there and it's monitoring the response or the output of the device under test. And that's sitting there passively checking and making sure that the test is progressing normally. And then we would also implement some type of functional coverage into our instrumentation around our design under test. So the benefits of this system are, next, Peter, I think there's some more things, is that really that the functional coverage is the measure of the verification completeness, and that we're keeping the stimulus checking and coverage all as separate concerns. I mean, we don't need UVM to make this work, but UVM is pretty much the industry standard way of implementing constrained random test. Next, please. And here's a diagram that we lifted from a article on using system Verilog for constrained random testing. And what it's supposed to show really is that that you're getting some time savings in terms of your coverage closure when you're using constrained random, as opposed to just having some kind of linear closure curve by just adding more and more directed tests into your suite. But what it doesn't really show is the additional quality of verification, the sort of the ability to find bugs that you'll get from constrained random that you won't get from directed. And this is an important sort of consideration when you're moving into constrained random methodologies, is that that you really need to you need to have your constrained random stimulus, your checking, automatic checks, and your functional coverage. They're all important pillars, but they're all separate concerns. So they're not sort of interwoven with each other. They're all completely separate things. You have to operate on their own. So that's just a useful sort of diagram to show that there, the importance of these different aspects of constrained random verification. So when we look at mixed signal, that's just the sort of general background of why we want to use constrained random. But we're mixed signal. We're typically verifying mixed signal designs here in Renesas. We've got a small example here that Peter put together, which actually shows a quite simple system. But it's quite typical of the sort of thing that we would do. We would have, in the diagram, we've got two DC-DC buck converters, which can supply voltage to 4 LDO regulators. All of these things are configurable, and the LDOs can take their supply from either DC-DC converter. So there's a little bit of a spec here. So we've got two DC-DCs, 4 LDOs. Each LDO range from 0.9 volts to 2.5 in steps of 50 millivolts. So there's 32 steps there if you add them up. And each buck converter goes from 1.2 to 4.4 in steps of 100 millivolts, which is again 32 steps. So typically what you do in the sort of behavior of these things in our mixed signal designs is that we'll have some kind of sequencing that the power management device will switch these things on in a given sequence, and usually it's configurable. So the sequencer in the boot process will configure any of the DC to DCs to supply one or more LDOs by the switches that you see in the diagram there. And there is a constraint there to say that each of those DC-DC converters always has to be have at least 200 millivolts headroom above the highest LDO setting. And also the startup order requires obviously the DC-DC converter to start before the LDO regulator it is supplying. And the LDO voltage could be anything within range. So quite a simple system there. But when we start to look at the verification of it, we'll start to see it's not, in order to do some exhaustive verification on this stuff, we start to see it's actually quite a large space that we need to verify. So if we look at the verification space, just purely in terms of the configuration, 6 bits for the LDOs, that's 5 bits for the V cell and 1 bit for the supply, selection, which buck is supplying it. That's 24 bits. 5 bits for the V cell on each of the DC-DC converters, and slot sequencer that was 3 bits times 16 So allow you to each slot would have a 3-bit select. I'll give you up to 8 potentially, but it will be enough for our system there. So if you add all those bits together, you've got 82 bits, which is a state space of 2 to the power of 82 combinations. So even if you could run through those combinations at 100 megahertz, it would take probably more time than there has been in the universe so far. So actually, you need to sort of put in the bin the idea of going through brute force testing these things, and you need to think about another approach. So this is where the constrained random comes in again. So this sort of methodology here is that we're using a spray and pray approach, as we call it. We're throwing darts randomly, well, hopefully in a nice directed way at the dartboard here, and we might get a bullseye if we're lucky. And what we're doing is we're using the CPU horsepower to generate many random test scenarios using the constraints we've put in place. So the constraints allow us to guide the automation based on our knowledge of the system to target the areas that we think we need to focus on, the corner cases, for example, where we think there are risks that the design might have a bug. Then, in order to go through and see how much we've verified, well, we create some what we call functional coverage model based upon the features and the parts of the specification that the design has to exhibit. So there's sort of the stimulus generation flow is that we put in place some declarative constraints. Typically, you feed those into a constraint solver, and then the constraint solver basically is controlling a random number generator, and that generates your actual numbers that go into the simulator, into the stimulus production. So if we look at the randomization flow, how does this sort of randomization tend to sort of affect a test and a design under test? How do we sort of use this in practice? So typically what we do is we'd have some kind of configuration object. So we system Verilog object or UVM object that carries our configuration for the test. We randomize it to get some test settings out for a particular given test. Then we use the checker would look at those test settings to say, okay, I need to use this configuration for this given test instance. And then also we need to apply those settings into the DUT configuration. And then we run the test and see if it passes or fails. So Peter came out with a very good example of this, which is, okay, if we're trying to explain it to some of the guys that are working in the mixed signal space who were not convinced about randomization. Let's say we have a cruise control system. The configuration object is holding the cruise speed. We randomize it for a test. That comes up with 56 miles an hour for this particular test. So our checker needs to be configured to measure the speed. Of course, it's got a tolerance. So, the checker will fail if the speed goes out of tolerance by 10% of 56 mile an hour. The DUT picks up that configuration. It sets its cruise speed to 56 mile an hour. And when we run the test, we ramp the speed of the car and we measure it when it's stable, and then the checker would say, okay, it would pass or fail according to the design behavior. So if we go back to the previous mixed signal example and how we might implement this in UVM, we could have a system configuration object called syscfg, which then holds multiple rail configuration objects. So those rail configuration objects are generic for any of those DC-DC converters or LDOs. So inside the rail configuration object, which we will have an array of, we hold things like we'll have an ID, and then we'll have a supply selection, we'll have a voltage selection, so the supply is which bucket comes from, and then we'll have a slot number. So you can see that everything apart from the ID, which we will assign programmatically, has been declared as a random. That means we can apply constraints on them. So you can see we've got two constraints at the bottom of that object, which will constrain the V cell inside a range. So we know that V cell is only ever going to be 0 to 31. That's our 5-bit configuration. And the slot range is only ever inside 0 to 15. Those are the legal slots that any supply can be activated in. Then this rail configuration, as we can see from the diagram on the top right, is a composition. So we'll have an array of these inside our system config. So in order so the sysconfig object contains a essentially a dynamic array of rails. We give it an attribute called numRails, which is randomized there, but in this system, of course, it's just going to be fixed to 6. And we have a constraint on there which constrains the size of the rails array to be the number of rails. What that does is when we randomize this system config, it will actually then create an array of rails of that size, but it won't actually populate those rails. They will be null. So we'll have to actually populate those rail configuration objects, which is seen on the next slide. And in order to do that, we use this, we hook into something a little bit more tricksy, which is we have a hook called post randomize. So it have to be called randomize. So then the array of rails with the right requisite number of objects has been created, but we need to then go through and use new to create a new rails object at each location in this for each loop. And then when we randomize each one of those rail configuration objects, we then have some inline constraints to determine how they're going to be, the numbers in there are going to be solved. So for example, the first one will actually is an ordering constraint to say that, well, we need to solve the supply before vcell because we need to know which DC-DC is supplying us before we can actually determine vcell, because we have this headroom constraint to say that vcell can't be above the DC-DC supply. It must be below it by 200 millivolts, in fact. The second constraint in the list there is basically saying that it's a implication constraint. So what it means is that in that list, if our ID is greater than 1, so we are saying that 0 and 1 in our array are actually going to be the DC to DC converters. Anything above that is the LDO. Then we are going to configure the rail to be either DC-DC 1 or 2, which is actually 0 or 1 here. And then we have another declarative, implication constraint underneath that one, which is the headroom constraint, which will say that the vcell of any of those rails which has an ID greater than 1 must be less than the supply rail, which is rail I supply. That's the supply number, vcell plus 2. That gives us our 200 millivolts. It must be less than that. And then the last constraint we have is to set the slot to be greater than the supply slot. So that means it ensures that the DC-DC converter which it is supplying is switched on before. So that's not particularly complicated code. It takes a little bit of talking through. I might not have talked through it particularly well, but what I'm trying to demonstrate here is that we have quite a complex system with a complicated number of dependencies there, but we're able to quite succinctly put together some constraints and randomization that will solve that for us and will reliably give us, random numbers constrained that will satisfy these system constraints. So we can see some example output. So we've actually only been discussing randomizing integers at that point, but the IEEE 1800 2023 LRM actually does introduce randomizing real numbers. So you can randomize a real. Now, if you randomize a real, the distribution is uniform across the range. For example, if you have a constraint C for a real value V, which is constrained to be greater than 0.0 and less than 2.0, then the probability of choosing a value in the range 0 to 1 is the same as probability of choosing a real value in the range 1 to 2. So it's uniform across that range. But I think the point at the bottom here, which I might ask Peter to explain with a bit more detail, is to say that you have to be careful about the numbers that are generated because of the resolution or the precision of your analog solver.
Yeah, so the digital can generate these wonderful 64-bit numbers, but there's no point in having accuracy below, say, microvolts, because most analog solvers have tolerances that anything below a microvolt difference on iterations is ignored. So you do need to put sensible clamping. Here I've done a microvolt, but actually I would have probably chosen 10 or even 100 microvolts as maybe being the rounding point. And this can make problems, create problems if you do automatic checking and you randomize a reel to 64 bits, apply it to the analog. It might be that you know that voltage won't come back because of the tolerances.
Thanks, Peter.
Yep.
Thank you. Okay, so just like we had some constraints on the integers, we can apply constraints to real numbers. So in this class here, I've declared a couple of constant values in there to make those constraints a little bit more clear. So we've got various values, low, min, nom and max, and we've got two numbers in there, real A and B, which we are going to be able to apply constraints to. So the constraint on the right hand side there is basically giving a distribution constraint. So it gives a weighting distribution to any of those values. So you can have a value in there, for example, the Z state value minus 100 has a weight of 5, and then you can have ranges. So those ranges are from, for example, a value low to value min, and that has a weight of 1. So that gives you the weighting, the probability of hitting that range or single value will be the weight divided by the total of weights you have in the distribution statement. And in the second example, there's similar a similar distribution constraint, but we also have a implication constraint there. So we're basically saying that if A is inside a certain range, value low to value min, then that implies that B is set to Z state. So we can have implication constraints for real numbers, and also we can have this. We would also probably have an ordering constraint there. So you'd solve A before B because you need to know what A is if it's inside the value low to value min to then apply the constraint on B to be Z state. So that's the randomization side of things, but we also need to think and consider coverage, because typically we might need to cover some aspects of the mixed signal DUT setup or some measurement apparatus, the sort of things that Peter is going to talk about in the second part of his presentation. So we can do this again in the language it allows us to do is so we can cover a range of real values, but we just need to remember that a range of real values is different from a range of integral values, because within a range we have all possible values within that specified range. So it's essentially an infinite, possibly an infinite amount of numbers that could go within that range. There is a cover group option real interval which actually defaults to 1, which defines this partitioning on a range of bins. So you could have a single value real bin that can fail to cover numbers very close to the bin value. So we had imagine we've got a 1.36, then the real number representation has a different precision, so we wouldn't hit it with a 1.3. So we have to be careful and consider this when we're building these cover groups. So here's an example of a cover group for a real number with a real interval of 0.1, and we have these bins. So we have a automatic range there, and we have a particular bin for a given value, a Z state value there. And you can see on the right hand side the tool produces the coverage results for the ranges, and it has a special notation to say that the square bracket is square parentheses is sort of inclusive of the number, and the round parentheses is exclusive of the next number going up. So it's splitting it up to this range 2.3 up until but not including 2.4, and the next bin is 2.4 up to but not including 2.5. So that's what that means when we look at that diagram.
Just on that, the users have to be careful with this, because you could get a nice report out saying you've had 100% in all these ranges, but it could be that this one here, it's only chosen 2.3 and nothing else, but there's actually a bug if it's 2.35, because with real numbers you've got sort of an infinite number of data points that you could try. You've got to be careful when looking at the coverage grade, that it could give you a false sense of security.
Thanks, Peter. So the metrics are important. The constrained random can cover more verification space simply by the fact that we've got automation when we're handing this over to our CPU farm. but we need to create a metrics model based upon the spec features and design knowledge, which is typically that's our functional coverage model. Another point that we quite often find is that because generally we find bugs when we get two things interacting together, that's quite a common source of interesting behavior, then actually putting pairwise crosses between features is quite a useful strategy in your verification plan.
So this is all great, but when it comes to AMS, we've got this problem that AMS is slow, and applying these techniques directly to AMS simulations is, although it is possible, it's not optimizing the setup, because really we only want to run a handful of AMS simulation because they take a long time. What we want to do is utilize DMS or real number modeling as much as possible because we can get a big performance out of that. So what we would do is you would run all your regressions using DMS models and checkers. So that will run in a fraction of the time. You can then look at the tests, and from each test see which one gives you the most functional coverage, which is a useful way of then working out which ones need to run in AMS, because that gives you more toggles, more things are happening. Then we can use the seeds that generate this also in AMS. So you're basically using, you've got the constrained random to give you as much spread on the dartboard as you want, but then what we're doing is then filtering those results so that when we come to run the more expensive AMS simulations, we've chosen them carefully. And what this works best in is if you can have a unified test bench for DMS and AMS where you can share all your test cases and collateral. And this was presented probably about 3 years ago at Verification's Future. So from that, we're going to move on to something slightly different, but with all of this checkers, what we often want is some sort of concurrent monitor for voltages and currents if you're doing DMS and AMS. So back to the example where you've got the DC-DC LDOs, you can do all the digital checking to make sure is all the sequencing right and all the rest using binds and probes, but you also want to be able to check the output voltage. So the idea of this was, we wanted the ability to monitor internal nodes in the design as well. We also wanted to monitor external nodes, and it to work irrespective of the netlist abstraction. So if your LDO was a DMS model, it would work without having to change any of your code or any of the functions. If it was AMS, it would work as well. And also support the fact that the node might not exist. So I don't want my test case to be full of if-defs. If this LDO is not in the design, don't include this test. I want to be able to write a simple test case that behind the scene, this function or what I'm about to present will just deal with it cleanly. And normally, from a verification point of view, you don't want to be probing too much within the design, but sometimes you can't always see the effects of subtle changes externally. So a reference voltage going to something like a DC-DC, it could get a big kick when the DC-DC turns on. It might then not affect any circuitry where you can look on the .ios to notice the response because some sort of analog filter has meant that you don't see it. But seeing that kick happened is vital because it's a verification hole that you don't know about. So being able to monitor it and go, hey, there's been a kick on that shouldn't have happened, means we can trap things before they get into production. So we want to be able to monitor voltage, port currents, power. So here's my wish list. When I come to build these things, I don't want an elaboration error if the path doesn't exist. So I want to be able to pass a string to a scalar node or port. And the nice thing about that is then I can make it up dynamically. The test case can call it. I want it to work seamlessly in DMS and AMS, so the user does not need to worry about the abstraction of the net that they're pointing this to. It basically is dealt with automatically. They just call this monitor and it just deals with it. We also want to be able to interactively change the trigger levels, the enable, disable, so the classic thing you might want to do is turn on when the band gap gets turned on. Once it's settled, is turn on a checker within thresholds and just leave it running until the band gap gets turned off. And you could do this for bias currents and other parts of your design where they should be fairly static values. That's what I've aimed it for. You could do it for envelope tracking stuff, but there's just a lot more work involved. Key thing with this is as you add more and more verification stuff on, you want to really limit the overhead to the simulator. And as a side product, the methodology I came up with here meant that we could use this for UPF supply monitoring. So we didn't need all the vendor extensions to try and get UPF working in a DMS or AMS environment. I was basically able to place one of this down. It would then tell the UPF whether the power was there or not. So as I just said, a useful one is the band gap. A band gap should be static at say 1.2 volts. You're unlikely to see the output of a DC-DC change if that gets a very small kick, because the response of the DC-DC will mean that it's just absorbed. But that kick could be catastrophic. And I have seen this before where we were able to see it externally, and it was basically a circuitry kick to reference so hard that the power reset kicked in. But imagine it didn't kick it hard enough for that to fail in simulation. That would have been really hard to find on the bench. So having this sort of dynamic checker that you can add in and that doesn't add much overhead would be very useful. So in DMS, probably this isn't as important as AMS, because if you've written your DMS model of a band gap, then you tend to have an ideal source with something that's just reading that value. You wouldn't model the kickback effects of when you turn on a block. But what you can do is run these things in DMS to pipe clean everything to make sure that you don't go and run it in AMS and find it fails, because it could have been 3 days into a sim, where in DMS you could have found that in 5 minutes. So this is the sort of thing you'd want to do. Turn it on here. This is the signal you're interested in, and when it goes out of range, get it to go and trigger an event so that the test case can do something, or it can report it to a user, automatically start probing extra nodes in the circuit to help aid debug. So the outline of the module is like such, where we have a system Verilog wrapper which connects to the API, and then we instantiate a Verilog AMS module and a system Verilog one for the DMS. This is pretty much the structure of UVM mixed signal as well. In the Verilog AMS one, we utilize the analog node and port alias functions. In the DMS one, we utilize VPI functions. So the user would set the node, so the string to the port or the net of interest. The mode would be, is it the voltage, current, or power that you're wanting? And I've added other ones to say whether this should work only in DMS or AMS only, or whether it should be there in both AMS and DMS. It could be that the net in question is in the depths below where you've written your DMS model. Therefore, you might only want to have it running when it's in AMS, just to speed things up. So there are 3 modules here. So what we do is, if I know I'm running a pure digital simulation, I basically have a system Verilog implementation of this module here that just is a dummy file that has ananode OK set to 1 tick B1. And that just ensures that you're running a pure system Verilog sim. You could leave that as Verilog AMS, but that would probably cost you a license from your EDA vendor. So it's just a sort of way of helping out there. And then you use the Verilog AMS one for those simulations. Right, I think we'll go through how this works. So the way a mixed signal simulation works, and if you go to the UVM mixed signal draft, it goes through this as well. The first thing that happens is the analog initial blocks are executed. And in my system, I check whether the string passed in, the node of interest, is electrical or not. And from that, it sets this anode OK variable. At that point, the simulator passes control to the digital initial block. It calls something called get anode OK, which uses upscoping from this module here to this one here to then read a variable in the Verilog AMS file. That's the only way you can do it, because you can't do out of module referencing, and you can't probe analog values outside a Verilog AMS file. So it's just a way of doing that. If it returns 0, then the node is the string that's been passed in is not electrical, or does not exist. So I then need to try to see if it's DMS using VPI. And if it is DMS, then I register a VPI callback. So if that net ever changes value, to come and trigger some code in the system Verilog land. And then if digital node OK is 0, then basically it doesn't exist at all. And then depending on whether you said it's AMS only, DMS only, or should be available in both, then you can choose what to do. At that point, you pass it over to the simulator to start the transient simulation, and you can then use the API to control the enable and the thresholds. So we'll just go over some of the boilerplate code that would be in the Verilog AMS block. So as I said, we use the $analog node alias, $analog port alias functions. Because these functions return a value to a variable called anode OK, and that is owned by the analog solver, we have to use a function to access it. So this function here, get anode OK, it has to take an input because that's part of the Verilog AMS LRM. It's still based on Verilog 2001. Returns the value of this internal node here, which is owned by the analog solver. So we set it to 0 to start off with in an analog initial block. If the mode is potential, it calls this function, sets anode OK. If it's flow, it does the same again using the port alias. Then once you start the transient sim, this analog begin and end allows us to have some monitor code that runs all the time, and you can optimize it by knowing if anode OK is 1 or 0. You could then turn the monitor on and off so that your analog begin and end is not executing code that it doesn't need to. And again, depending on whether the mode is potential or current, you can use the different access functions to access either the voltage or the current. So that's sort of what we put in the VAMS view. The digital one's more involved, and that's what we're going to focus on here. System Verilog has no digital node alias, port alias. Vendors don't have a generic one that will work with any net type, because you need to know what the net type is for these sorts of functions. Direct access using an out of module reference would cause in AMS a connect module, or in pure system Verilog a net type conflict, because you'd need to know the net type up front if you use an out of module reference. There's also no native current probing, so if any of you have access to this paper here or presentation will explain how you can use the VPI to get port current probes from a user-defined net type. Vendors provide various user-defined net types, and this is a way of getting the port current probe which they don't provide. You know, the way around all of this is basically you need to query the simulator at runtime to know what the object is, and then from that work out what to do. You know, so what we do is we use the VPI layer to query the simulator, and from that we can work out what to do. So the way you write your C program here, and that basically uses VPI routines that are supplied as part of the simulator to allow you to query it. So you can go and query like, what's the time scale of this module, and other things like that. And the nice thing about this is it's all LRM compliant. So the first thing we need to do is we need to create a callback. We need to give it a path and go, right, register this callback. So this is a custom C function called DPI UDN change callback. We write the C function and then we import it in. That will be the name of the C function. This is the name I've given the system Verilog function. And then basically I've written a wrapper around it just to do some error checking. So when I call this function here, I pass UDN net, which is a string. So that would be the hierarchical path to the UDN net I'm wanting to monitor. I've got a string called error message. So if anything goes wrong with my C code, I get it to return a string up here that I can then print at this point. The scope is quite important. The scope's needed to know that when this UDN changes value, where in my module or package or class-based hierarchy should I call the task that this event needs to do. And this function returns a 1 or 0. 0 means something went wrong, so it could be that the net didn't exist. So the idea is you'd call this to start off with by importing this. So that's the first part of the problem. You've now registered from the C layer, you want to generate a callback. Within the C layer, what we do is we use the VPI functions like VPI get handle by name. So that path would be the string that we would have passed in from here. That gets me a handle to that. I then iterate over it to look for different elements in it. This is very cut down of what you have to do in the VPI. But fundamentally, what I then do is build up a callback procedure and register it to the simulator. So in this case here, I've basically found the V element of this UDN that's on that path there, and this callback then says whenever the V element changes, it's going to generate a callback routine, and this is the data of the callback routine. So you give it the reason change, the callback C function it should call, and some other aspects of it. This you can pick up from some documentation. The callback, let's see if I've got it. The callback routine here does a very basic thing of getting the scope from the data that was part of this callback routine. It sets the scope. It then calls a templated function called DPI update UDN. That function is the opposite of the other way around. I'm basically saying this C function actually calls this system Verilog one. And so in this case here, when that's called in the C layer, it actually calls this task here, which then calls this bit of code here. And then I've done some optimization, because a UDN could be updated, say, 10 times in delta cycles. You probably only want to execute the always block once at the end, once you've got the final value. So this is the non-blocking event construct. So that will make sure that it only happens at the end. So then we're now onto the code for monitoring. I use an integer variable to toggle 0 and 1, so in range int a and 1, so that just says whether the monitor is within range or not. I don't use above or cross. The reason being is they enforce time steps in the analog solver, and to be honest, if the thing's gone out of range, I don't need it right at the crossing point. It makes no difference. There's something wrong. We have to add some hysteresis to avoid oscillations. And basically this sets this in range int a, that we use a Verilog AMS construct to sample the analog value and make it discrete again. And therefore we can use this discrete value in the wrapper cell to then create some message in the UVM area. So in the DMS monitor, we had the event, the node changed. Here I've expanded it, some other things. And then if node change triggers, we could then say is the mode potential or current. And these are some other VPI routines I've got that will take in the path and then return a value. And just like before, I can do the range checking on it. In this case, these are discrete variables anyway, so the wrapper layer can just probe these directly. And so therefore, in the monitoring level above, we have an always block. It will execute. If ananode OK, it then waits for this condition, which is looking inside the AMS monitor core for the in-range int toggle. And if it does, it will then either print out an error message or an info. Else you can get it to monitor on the dig node OK. Sorry, that begin should be down there to make it look easier. So this is just some optimized code, and it's written that way so the always block executes at time 0 before any event happens. It's just a neat trick to save initial begins everywhere. Over to you, Stephen.
Thanks, Peter. So given that we've got our constrained random stimulus and our nice independent checkers that Peter has described, we also need to have, if we don't have a good methodology, it falls on its face, unfortunately. So I think this section basically talks about, bringing it all together and what the sort of mindset we need to do. So, there's no point in trying to just simply, interoperate with the protocols that you're presented with. You have to try and explicitly do the bad machine testing, explore the corner cases, and have any design or spec inconsistency immediately flag that as being a bug. That's in terms of the sort of mindset. The reuse and the debug, you need to think about putting that into your verification environment right from the start. So that's using a methodology in the right way, and using the using the metrics in the correct way. So not just using test case passing, but collecting your coverage when your checks are in place. Coverage is meaningless without the checks in place. So bringing us all together really is the UVM mixed signal effort, which is standardization of analog mixed signals extensions for UVM. So you get all the goodness of UVM in the mixed signal space, and the metric driven verification suits this, due to the large verification space, even as we've seen on fairly small mixed signal designs. So it's called UVM mixed signal rather than UVM-AMS. It's called mixed signal because it supports any mixed signal system, DMS, real number modeling, SPICE, or a mixture of thereof. And randomization isn't mandatory in this system, and you get benefits even when you don't use it, because you have a standard methodology and you have a plug and play reuse of the existing UVM components. So here's the concept that Peter and I sort of essentially just developed, which is the canonical UVM mixed signal agent setup, the architecture, which basically is fairly similar to the standard UVM non-mixed signal, but we have some tricks in place in order to support a VAMS or system Verilog core, which is really the guts of our communication with the mixed signal world. So we typically send and receive information via a proxy class, which is inside a system Verilog bridge component. So it's organized in this way such that it's easily we can easily override the sort of nature of the components in it, and also it supports the various languages as they are at the moment in terms of communicating information between VAMs and system Verilog. And moving swiftly on to the conclusion. So the conclusions are that constrained random verification is definitely applicable for mixed signal designs, if not essential, but you have more you get the pain without the gain without the pain. But you can reuse stuff that you've spent times developing because you've got a plug and play methodology with UVM. We can also leverage DMS to select the best seeds for slower AMS tests for best coverage. And if you are using a metric-driven mindset from the V-plan onwards, that's when you get most success. If it goes wrong in the V-plan, you're guaranteed pretty much to fail in your execution. And Peter's VPI methodology for concurrent checking is a very powerful system for analog intent on signals, whether they're in DMS or AMS. And the verification engineers, in order to use this, don't need to know about the Dutch abstraction. And UVM-MS will be the vehicle to drive this capability.
So that comes to the end. I know we've overrun slightly, so that the time for the Q&A is limited, but are there any questions?
I see one in the Q&A box.
Yeah.
Peter.
So that's going back to the beginning example where we had the DC-DCs and LDOs. So yeah, these could have been SPICE models, they could have been VAMS models. It doesn't really matter. The problem you've got is just taking the digital control inputs. You've got a vast number of combinations to try. And yes, you can do them all with, you probably can cover a lot in the DMS modeling, but there will be a combination that maybe doesn't work too well in AMS. Or you could have a mixture of DMS, AMS models, and then SPICE. So it's now probably over to the people at the conference if there's any questions there.
All right. Thank you, Peter and Steve.
I think Christie's put her hand up for something. I don't know whether you can let her speak or.